Hello, my name is Matt, and in this video, I'll be talking about fast collision avoidance in the Grace Autonomous Racing Competition. In a racing environment, an autonomous car must be able to avoid obstacles safely while preserving as much speed as possible. If an autonomous car can do this, it should also be able to avoid collisions in real-world situations where braking is not the best option. For example, when avoiding a close stationary object at highway speed. In order to be as safe as possible at high speeds, we used a combination of methods. We implemented a PD steering controller, a track interpolation scheme, and an obstacle avoidance algorithm known as Follow the Gap. This algorithm will be the primary subject of this video. Follow the Gap works by observing all obstacles in front of the vehicle and structuring the environment as an array of gaps between those objects. These gaps are measured in radians, and the algorithm works by aiming the car towards the center of the largest gap. In theory, this should lead to maximum safety at speed. Here we can see how the Follow the Gap algorithm views the world as it navigates obstacles. In the top left visualization window, the yellow and green dots mark the respective left and right bounds of the largest gap. The pink dot marks the center of the gap, and this is the vehicle's target location. Notice how the left bound of the gap changes locations as we pass the first car, and the right bound of the gap changes from the track limit to the pedestrian as they come into view. Here is another real-time example that shows how the Follow the Gap algorithm can easily make passes safely within complex environments, with obstacles traveling at different speeds and directions. Now we will see some footage from the Grace competition itself. From the first race, we will see that the Follow the Gap algorithm succeeds in what are essentially base cases for any obstacle avoidance algorithm. The first challenges consist of single obstacles or very small groups of obstacles, both on straight sections of track and sections that are curved with elevation change. Follow the Gap has no problem staying on track and avoiding these obstacles. At the end of this clip, we can see that the vehicle fails to avoid a collision. This is because our controller was not programmed to brake hard enough to avoid this collision. However, this also shows that in a real-world failure such as brake failure or a stuck throttle, Follow the Gap would be useful in minimizing danger, as the resulting collision was a side-by-side glance rather than a head-on collision. In this example, we can once again see that our controller is able to avoid collisions in complex environments with larger groups of more diverse obstacles. Now we will cover some higher level results. First, we can compare our controller to the Grace baseline. In 3 out of 5 scenarios, our controller was able to beat the baseline controller by a consistent and significant amount. In Grace, a lower score is better, as it means that a controller was both faster and had less collisions. In Scenario 1, our PD controller gains that were tuned for larger vehicles had a hard time matching the small BMW iZeta, and thus led to a higher score. In Scenario 5, there are multiple sections of track where there is no gap to follow, and the controller must slow down to the speed of traffic. Since our controller was not programmed to do so, it suffered a greater number of collisions than the baseline controller. Because our obstacle avoidance algorithm allows for higher speed, our controller was able to attain a higher average speed than other controllers. In 2 races, our vehicle was the first to finish out of every competitor. We were also able to drive faster than many other controllers. This means that our controller was able to place second in the Grace head-to-head competition, which did not include obstacles besides the opponent vehicle. Overall, I had a great time in 484. Learning about control and planning was extremely interesting and entirely new to me. Even though our project wasn't on hardware, getting to see the GEM vehicle and the high bay was really exciting, and the MPs were pretty fun as well. Learning about high level planning concepts really helped us in our final project because we knew what planning algorithms would and wouldn't work for our application.
I mean, I think what benefits the most was thinking about the safety and planning, of course. The MP were pretty well structured. They were challenging. There's some learning curves, but definitely be rewarding once you complete them. And something I learned a lot is to think about optimizing things like the path that we can take or even the controls on the vehicle. These minor tweaks that will help in our outcome in terms of the vehicle. I really enjoyed learning about the stability of the states. So what kind of control would help our vehicle reach to safe state or unsafe state. And I think those are the kind of the higher level that I can take out of the semester and utilize it for different parts of the robotics and autonomy.
What I really like about the course is that the things that we learn in the course, although it's very like there's a lot of theory and a lot of calculations, but everything we learn in the course can be applied in a real autonomous car that like big companies are building right now. And I really enjoy our now where we got to learn about how to measure the safetyness of cars and when there are guest speakers also talking about how to develop autonomous system for race car. I think all of them are very interesting, and anyone who is interested in autonomous vehicle and system should be taking this course.